Solving a trigonometric equation modeling a real-world situation. We already know how to solve a trigonometric equation, so let's get the real-world situation here so we can model it. For a fixed location, the number of sunlight hours in a day fluctuates throughout the year. Suppose that the number of sunlight hours in town place can be modeled as this function. L of t equals 12 plus 2.7 times the cosine of 2 pi t over 365, where t is counting the number of days since June 10th of this year. On which of the first 365 days will there be exactly 10 hours of sunlight? Or probably there will never be exactly 10 hours in one particular day, but we'll get as close as we can in the first 365 days. So, a lot of information here, most of it fairly useless to us, beauty of mathematical modeling. So let's take a look just at this function. And remember, we're looking for the day at which there are 10 hours of sunlight. So I want to set this equation equal to 10. And we can do some pretty simple rearrangements here. Subtract 12 on both sides of the equation. Negative 2 over 2.7 is the cosine of 2 pi t over 365. Now here, before I continue onward, I want to think a little bit about my domain. I was asked to find the days in the first 365, which means that 0 is less than or equal to t is less than 365. Or to play it safe, we might want to do less than or equals on this side as well. Now, my argument on my function here, 2 pi t over 365, if I multiply both or all three sides of this inequality by 2 pi, and I divide all three sides of this inequality by 365, I get that the argument of cosine is somewhere between 0 and 2 pi. Very convenient. These are the places that we normally are looking for when we're looking at solving trigonometric equations. So my next step is going to be to do a Usubstitution. And the point of a Usubstitution is just to find a new way of writing your argument of your function so it's a little bit easier to work with. Right. I like this particular substitution because solving trig equations where I'm looking for solutions between 0 and 2 pi is kind of the standard of solving trig equations. I also greatly prefer solving trig equations when I'm solving for the argument of the function and not other stuff going on. So negative 2 over 2.7 is the cosine of u. I will grab out my calculator at this point and evaluate the inverse cosine of 2 divided by 2.7. As I often do when I'm working with my trigonometric functions, I'm going to ignore the fact that I have a negative value here and deal with that after I find the value of the reference angle. I get here that my reference angle is going to be 0.7, well, around the nearest thousandth, 0.737, and that's in radians. I also know, looking at this, that I'm dealing with a negative value of cosine, and negative values of cosine occur in the second quadrant and in the third quadrant. So I might have that as 0.737, or I might have that as 0.737. Now u, measured from the positive x-axis, is going to be one of these two things. Either it's going to be pi minus 0.737, or it's going to be pi plus 0.737. Those come out at 2.405 or 3.879. These are the two possible values for u between 0 and 2 pi. And as we saw on the previous page, if we keep u between 0 and 2 pi, that will ensure that t is between 0 and 365. So now, let's grab all this information. I know that u is 2 pi t over 365, and I've figured out that u is either 2.405 or u is 3.879. So by substitution, that means that 2 pi t over 365 is 2.405, or 2 pi t over 365 is 3.879. Now, solving for t, multiply both sides of the equation by 365, divide both sides of the equation by 2 pi, and again, as always, be careful punching things into your calculator. You probably need that 2 pi in parentheses. But we'll round to the nearest whole number of days at this point. 139.710 rounds to 140. And 225.337 just rounds to 225. So on day 140 and on day 225, there should be 10 hours of sunlight.